This video looks at properties of multiplication with matrices. The previous video looked at how you multiply matrices, and here what we're going to do is focus on some useful properties that are linked to the multiplication operation. First, a reminder then of what's the generic formula for multiplying matrices. What we told you in the previous video is if C was given by matrix A times matrix B, then the coefficients of C, so C, then I, j, are given by this formula here, where you'll notice you take the ith row of A and the jth column of B. So the ij element of the result uses the ith row of the left-hand matrix and the jth column of the right-hand matrix. The result, that is the matrix C, has got a row dimension of A and a column dimension of B. So that was in the previous video. And we also noted in the previous video that because of this definition, in general, AB is not going to equal to BA. And if nothing else, you can see that from the dimension statements. In fact, it's quite common that AB will exist, but BA will not, or vice versa. So first property then, prove that both pre and post multiplication of a matrix by an identity matrix results in no change. So a typical identity matrix is given by something like this. Here you'll see I've given a 4 by 4 identity matrix. I'm going to use capital I to represent it. Now, the formula for multiplication is given here, and you'll see I've said the matrix C is the product of a matrix A post multiplied by the identity matrix. So I've simply substituted in the standard formula for matrix multiplication. So C I, j is given by A I, 1 times capital I 1, j plus A I, 2 times capital I 2, j, and so on. So there's your standard formula. But if you look at this identity matrix, you'll notice the only non-zero values are on the diagonal. So that's where the subscripts are the same. And therefore, capital I, j is 0 whenever little I is not equal to little j. Now if I substitute that observation into this top equation, you find we get this, that C I, j is given by A I, j times capital I j, j, which clearly is just Aij. And if you haven't seen the obvious there, Cij equals Aij. C and A have the same coefficients in the same places. A similar proof can be worked for pre-multiplication by the identity matrix, so we'll let you do that by yourself. Properties 2. Prove that AB equals 0 does not imply that either A equals 0 or B equals 0, and clearly that's very different from the result you would get with scalars. This can be demonstrated with a simple example, and the view we're going to take is if you can show it works for a simple example, then it will obviously apply to many others. Here's a simple example then. You'll notice I have a non-zero row vector and a non-zero column vector. And if I multiply these two together, the 3 times the 2 gives 6, 1 times 4 gives 4, 1 times 4 gives 4, minus 2 times 0 gives 0, and 7 times minus 2 gives minus 14. But if I look at that sum there, I've got 0. So I've multiplied two non-zero vectors, but the result is 0. Here's another example. And you'll see this time I've multiplied a row vector on the left by a column, by a normal matrix on the right. So what we've got is we've got 2, 2, 2 on the left, the first column 4, 0, minus 4, I multiply those together, I get 0. The second column 6, minus 3, 3, and multiply that with the row vector, and I get 0. So again, I've used non-zero matrices, multiplied them, and yet I've ended up with 0. Now just a note at the bottom, vectors whose product is 0 are talked about as being orthogonal, but that's a topic for a different video. Prove that A times BC equals AB times C. So what are we trying to do here? We're trying to say that the order in which you carry out the multiplication does not affect the result. Now that's really important because A, B and C are matrices, and so you might be thinking, well, if I do AB first and then multiply by C, if I do BC first and then multiply by A, I might get a different answer. So we need to check and confirm that you don't. Now the algebra here is a bit messy, but it's not as bad as you might think. So let's do one line at a time. This top line, I'm going to do AB first. So all I've done is I've written out the definition for the coefficients of D using the formula for matrix multiplication. So the ijth element of D is given by the formula there in the red box. Now, having found AB, next what I'm going to do is post multiply by C, and I'm going to put the result in E. So if I post multiply by C, then again using the standard expression for matrix multiplication, you can see the coefficients of E depend upon the coefficients of D, because D was AB, and the coefficients of C. And then the final step, what I'm going to do is I'm going to take the coefficients of D from this top box and I'm going to substitute them in, wherever appropriate, into this second box. So if you look on the line below, you'll see what's in the round brackets here is simply the expression di1. So I've rewritten the expression for E but substituted in from the top line. So it looks a bit of a mess, but the key thing is you can write an expression which says what are the coefficients of E, I, J, and how do they depend on the coefficients of A, B and C. So we have an explicit expression. What am I going to do next? Next I'm going to do it the other way around. So first I'm going to multiply B and C, and I'm going to call this F. So again, you'll see in this top box, there's the matrix multiplication definition, which gives me the coefficients of F. Then I'm going to get E again by pre-multiplying BC by A. So once more, I use my standard definition for matrix multiplication, there it is, and I simply plug in the values for A and the values for F. Now you won't be surprised about the next step. I take the coefficients of F, which I got at the top, and I plug them in to this expression down here. And so therefore what do you see in this bottom line? You'll see these big brackets where all I've done is plugged in the expressions for F1j, F2j, and so on. Now what's the bottom line? I now have two alternative definitions for the coefficients E, I, J of the result A, B, C. And what I need to do is ask myself, do these give the same result? Now I've put here clearly they are the same formula. Actually what you're going to have to do is multiply these out longhand and it will become apparent that they are the same formula. I don't really want to do that here because it would take lots of time and lots of space, but you've got the two formula written down, and you could, for example, you could say, right, I'm going to focus on the A1i and see where does A1i appear in this top expression, and then you could say where does A1i appear in the bottom expression, and write all the terms out, and you'll see they come to be the same. And you can do that with any coefficient you choose. Properties 4. A matrix can always be multiplied by its own transpose. Matrix A has got dimensions r by n, and matrix A transposed has got dimensions n by r. So therefore, if you want to do A times A transposed, then on the left you've got r by n, and on the right you've got n by r. So clearly the two adjoining dimensions, the column dimension of the left, the row dimension of the right, are the same, so you can do the multiplication. What if you do it the other way around? A transposed times A. Well, now of course on the left you have n by r, and on the right you have r by n. So once again the adjoining dimensions, the column dimension of the left, the row dimension of the right, are the same. They're now both r. So both A transposed and A transposed A are always defined. And properties 5, commutativity. Matrices are said to be commutative if the following property holds. If AB equals BA, that's if you change the order of multiplication, you still get the same answer. Now, the conditions for this happening are quite restrictive and it's very rare in general. I wouldn't expect it to happen for most problems that you come across. And it should also be obvious that in order for matrices to be commutative, they must be square. Because if they're not square, then the dimensions of AB would not be the same as the dimensions of BA. So summary. We introduced some key properties linked to matrix multiplication. We looked at the impact of multiplication by the identity matrix and seen that it's nothing. The possibility of the product of two non-zero matrices being 0, and that's quite common. The insignificance of the order of multiplication when you have many matrices multiplied together, and the concept of commutativity.